This is question 5 under problem set 4. A pullback car with a mass of 50 grams is pulled back a distance of 0.3 meters. After being released, it reaches a final constant velocity of 12 meters per second. Assume friction with the table is negligible. No thermal energy. Draw state diagrams for these 4 states. Pullback car is at rest before the person has pulled it back. The person has pulled the car all the way back. The moment the car reaches a velocity of 8 meters per second, the moment the car has reached its final top speed of 12 meters per second. Recall that the car has a mass of 50 grams. And because I know that I'm going to need the mass in kilograms in order to calculate things here, I'm going to go ahead and calculate that. 50 divided by 1,000. That'll be useful. Let's now figure out the energy situation here. Before the person has pulled the car back, the car is not moving, it's not elevated off the ground, it has no elastic energy. Zeros all the way across. By the way, you'll note that all the way across here, I didn't include EG, gravitational energy, because we never change elevation. If it's never going to change, it doesn't matter. Just leave it off. Later on here, though, I know that the car has some amount of energy stored in it. We've wound up the spring. That tells me 2 things. Number 1, there is elastic energy and therefore system energy in the car. The number of blocks I choose is not important, but I'm going to try and keep their approximate number of joules per block constant across the page here. So the number of blocks is not important, but you want to kind of keep them in mind as an approximate size. The second thing that this tells me is not only elastic, it tells me some energy had to come into the system. No energy, 2 blocks of energy. Somebody's doing work on the car to introduce this much energy into the system. We'll calculate the amount soon. You'll note that I'm considering the car by itself as its own system. I'm not in the system, so me pulling the car back, I'm introducing energy into the system. In this next state, the car is moving and the spring must not be fully unwound yet because it's still got more speed to pick up. So in this state, I'm going to show a little bit of elastic energy and I'm going to show a lot of kinetic energy. Now I'm realizing a flaw in my approach here. Only having 2 blocks means that I would need to 50-50 these, and I don't really want to do that. So I'm going to just go back and modify this. So let's do lots of kinetic, very little elastic. I need now 5 blocks back here because we don't know work happen. This is the problem with just picking the number of blocks at the beginning. If you're not sure where it's going to go, you might need to juggle them around a little bit. All right, so the elastic energy is it's transferring into the kinetic category, and the car is speeding up, and we've still got the same amount of energy here to here. Now, how about that last state? The car is at its top speed. I'm going to presume that the spring has fully unwound and that we haven't introduced more energy. Let's keep it at 5 blocks. All kinetic. No elastic. Right. This is the only state where work is done. This is the only place between 2 states where work is done. We're told to make this a quantitative energy flow diagram. I want numbers at the tops of all these stacks. So I'm going to look at where should I attack the problem first. I'm looking for ideally a state where I've got only one type of energy. It's probably going to be easier to calculate. So that's here or here. So I'll write down the relevant calculations for these. This is only elastic. And over here, only kinetic. Which one do I have enough information to calculate on? I do know the mass of the car, and I do know how fast it's going. This one is a good candidate. Check back here. I don't know the spring constant of the spring inside the car. I do know how far it was pulled back, so I can't do this. This is the place to start calculating. .05 for mass. Velocity was given, 12. Don't forget to square it. Calculate time. That comes out to be 3.6 joules. And I recommend add that to the top of the stack. I'm just going to assume all these are energies, they're all in joules. 3.6 joules of kinetic energy by virtue of mass and velocity being known values. The only type of energy here is kinetic. That means the total has to also be the same, 3.6. Look across your page here. Is there anywhere that the amount of energy is constant? 5 blocks in my case. Yes, yes, yes. Every one of those stacks gets a 3.6 at the top. Ooh, almost stopped there, not there. One final thought is the amount of work we did. 3.6 joules came in. This is what it means to do a quantitative energy flow diagram. The only thing that's missing is I don't know the distribution here. Let's calculate that. Can I calculate either of these stacks out? Yeah, it looks like the second one. 0.05 again. We're told the velocity. .5, 1/2 times 0.05 times 8 squared. 1.6 joules. 1.6 joules of kinetic energy. Throw that atop the right stack. How much elastic do we have then? It's going to be the difference between 1.6 and 3.6. Oh, that's 2. Oh, this highlights a problem in my assumption earlier. I was like, oh, lots of kinetic energy, not very much elastic. Totally didn't work out that way. I'm going to revise just because I can here. Maybe we'll do 3 and 2. So it more accurately reflects reality, right? All right. Good, we've quantified all the stacks on here. You're done with part B, drawing a quantitative energy flow diagram. Part C, what average force did the person apply to the pullback car? And D, what was the displacement of the string? Average force did the person apply to the pullback car? This is an idea that we have not yet learned. So I'm going to show you that. And it relates to this work quantity. So we'll bring that down here. Work changes the amount of energy in the system. That's one definition. It is also defined as a force applied over a distance. It's the product of those two. One big caveat, that force and that distance have to either be going in the same direction or opposite directions. Parallel to each other is what's important. How's this useful? How much force did the person apply to pull back the car? How hard was it to pull back? Well, do I know how much energy came into the system or how much work was done? Yeah, totally, 3.6 joules. I'm being asked what the force is. I don't know yet. Do I know how far the force was applied over? Like how long this person was pulling on the car? Oh, yeah, it turns out it's that 0.3 meters. This will be 3.6 divided by 0.3. I get 12. It's a force, 12 newtons. 12 newtons, part C. What was the displacement of the spring at state 3? Okay, I didn't use this equation up here, but now we're going to. You know what? I'm going to need a little more space. This is going to go away for just a second, sorry. What was the displacement of the spring in this state? I need to know X. I know the amount of elastic energy, but I don't know K. I don't know the spring constant. Where else does the spring constant show up? Can I get it from there? Yeah, totally. It's over here. All right, we're going to go pause this. We're going to go over here to get K first. Elastic energy in this state, 3.6 joules. The amount of stretch in the spring at this point, 0.3 meters. Don't forget to square it. To solve this, I'm going to do K equals 3.6 times 2 divided by 0.3 squared. Okay, let's do that real quick. 3.6 times 2 divided by 0.3 squared. I get 80. Units of K, newtons per meter. Oh, that's not technically a question. I'll need a box around that. K is 80 newtons per meter. We're going to bring that up here. Elastic energy in this state, 2 joules. Same spring in these two states. The K remains constant. That's the whole point of spring constant, 80. How much is the spring displaced in this state? That's what this question's asking for, is X. Let's solve this for X. I'll start with X squared. Rearrange, divide everything over here. 2 times 2 divided by 80. Square root of all that. Four divided by 80. And then take the square root of that. I get about 0.22 meters, or 22 centimeters. That's the answer to the final part of question 5. What was the displacement of the spring? Having the quantified Lowell diagram makes this a much, much simpler problem to solve. I strongly recommend